Hello, and welcome to a new lecture on Cantera. This will actually be the last lecture in the series for reaction kinetics. And today we will look at some functions. Basically, I can broadly divide into two categories. The first set of functions will tell you about the rate of reaction. The second set of functions will tell you about the heat released in all these reactions. So let's jump on to the first set first. For that, we will have to first select a reaction from, say, the GRI mechanism so that we can test out these functions. And this will be done on the Python console. Let's start with importing Cantera. And let's define an object. Okay. Now, in the previous lecture, I think we chose reaction number 11. So let's just go ahead with that. We can actually do any one. So let's first take a look what reaction 11 is. So gas dot reaction equations. The index will be 10 for reaction number 11, which is this. So in the GRI mechanism, the 11th reaction is CH4 plus O gives CH3 plus OH. And so let's now set up some amount or some composition for these four reactants or these four species to look at these to look at the use of these functions. So what we will do is we will first set up some composition for each of these species so that there is some reaction that can start. So let's say gas.tpx equals, let's say 300 to start with, CT.1 atmosphere. And this can be, so CH4, let's put it at something like point, so 1. Then there is O. We can anything to 0.5. Then there's CH3. Let's put that as like 0.2 something, and then there is OH. Let's put that at 1. This is just randomly what I've chosen. All right, so now if we look at the gas, see you have all of these four components. So this is the composition of the gas at this point. And again, the reason why we let's go to the equation, to the function, and then we'll understand what has been done here. The first function that I want you to know is called gas dot forward reaction rates. Okay, and this needs index of the reaction, so reaction number 10. Oh, sorry. There's no attribute. Oh, I'm sorry. Forward, it's called forward rates of progress. My bad. Rates of progress, and we give the index of the reaction, which is 10. Okay, so basically, I mean, this is the name of the function to calculate the forward reaction rate is forward rates of reaction, and similarly for the reverse reaction rate, it is reverse rates of progress. And what this says is if we have this equation, this reaction, CH4 plus O gives CH3 plus OH, with this particular composition of each of these species, then at 300 Kelvin and 1 atmosphere of pressure, this will be the rate of forward reaction. And the units is kilomole per meter cube per second. All right, now if we want to know the reverse rate of reaction, so this means that to calculate what is the rate of reaction when CH3 plus OH go back to CH4 plus O. So all we have to do here is just change forward rates of progress to reverse rates of progress. Okay. And similarly, there is also another equation which is known as net rates of progress. Okay. So this net rate of progress gives you the difference between the forward and the reverse. So forward rates of progress minus reverse rates of progress. So a negative net rates of progress would mean that the whole reaction is going from the product to the reactant side at this particular temperature and pressure conditions. Now let's raise the temperature, for example. So if we say gas of TP equals say 1000, comma, again, keep the same pressure. All right. Now let's again run the same exact equations or functions. Forward rates of progress. Now see, the number has changed from 0.325 to 4336. It's such a big jump, mainly because of the change in the temperature. The temperature jumped from 300 to 1000 Kelvin, which is again a very big jump. And now let's look at the reverse reaction rates. So for this particular reaction, the reverse reaction rate is only 121, and the net will be the difference between the two, which is 4215 kilomole per meter cube per second. Right now, there is another function that tells you the creation or the destruction rates of each of the species. So let's find out what is the rate at which, say, methane, CH4, is being produced or destroyed, rather consumed or produced in this equation. So that function is called creation rates. So that will give you gas dot creation rates. Okay. Let's do it for CH4. So gas dot species index CH4. Okay, so this is the creation rate. This is the rate at which CH4 is being created in this reaction. Let's look at the destruction rates of CH4 for this particular reaction. Sorry, destruction. Sorry, I blanked out for a second. And again, I think I mistakenly said for this reaction, sorry, these creation and destruction rates are for the entire series of reactions that are present in this reaction mechanism of GRI 3.2. So the destruction would be this much. And there is also a difference between them, which is net production rates. So we say net production rates. You see, so what this does, it takes the difference between the two. So overall, in this entire reaction mechanism, CH4 is being consumed, and certain other products are being made out of it. Now, if this reaction were, or this entire mechanism were to attain equilibrium, this is an interesting and important concept. So if it were to attain equilibrium, what that would mean that all the reactions in this entire reaction system have frozen. And they are, it's a sort of a state of suspension. So all the forward reaction rates will be equal to the reverse reaction rates. Everything is frozen in time in an equilibrium system, as we've seen in the past. Let's Let's take this system to an equilibrium state, and then let's see what is the interesting thing that happens. So we'll say gas dot equilibrate at constant enthalpy and pressure. Okay. Well, now just to quickly take a look, now see that all of these different species have been produced, and the temperature of the gas right now is at 2786 Kelvin. All right, now let's look at the net rate of progress. Now, net rate of progress for the 11th reaction, which was CH4 plus O gives CH3 plus OH, I suppose. Right. So let's look what this gives now, net rates of progress. See, the net rate of progress right now is such a small number, 10 to the power minus 22, which means that there is really no progress. I mean, the forward is equal to the reverse rate of reaction, and so the difference between them is almost zero. So that's there. And let's also look at the creation and destruction rates, or creation and the net production rates of CH4 again. So creation rates of CH4. So the creation rate is also a very small number. And when we go to net production rates, we'll see the net production rate is 10 to the power minus 19, which is again almost zero. So everything, there is no methane being consumed, there is no methane being produced, there is no net reaction rate of progress. It's just everything is just frozen, right? So this is how these, I mean, these were a set of some functions that help you understand what is the system doing in terms of its reaction progress, right? The last one is, we'll go through this quickly, and this one is on the heat produced. So let's write a small code using a reactor, and we'll advance the reactor to a certain time step. And then we will see what is the entire heat that was produced in all of those reactions. So let's say import. Cantera is already been imported. So Cantera is already there because we've imported in the console. We will need something known as NumPy, which is useful to work with NumPy arrays. And again, we will not go into the theory of NumPy and its arrays. We'll just use it here. If you are not familiar with NumPy and how it is used in Cantera, I highly encourage you to go and look at the theory for this. Import NumPy as NP. Okay. Now let's say gas.tp equals 1000. Or sorry, let's actually we have to still well, we already defined the gas, but let's still define it here too. So CT dot solution GRI 30 dot YAML. Still giving me an error. So that is mainly because the script does not know that Cantera has already been included in the console. But let's again, it's just for the sake of it, go ahead and import Cantera again. It will not harm us in any way. All right. Now, let's assign a temperature and pressure. .Tp equals 1000, comma CT dot 1 atmosphere. Okay. And let's set up the initial composition of the gas. So set equivalence ratio at say 0.77, which is a lean mixture in let's say CH4 O2 N2. Okay, so we've set up the composition, and now let's use a reactor. Let's use the ideal gas constant pressure reactor from Cantera. So R equals CT dot ideal gas const pressure reactor, and assign the gas object to it. And then familiar line, which was sim equals CT dot reactor net, because we will be advancing this reactor in time. Okay, and then we will say sim dot advance to say some 20 millisecond or something. So 0.02. Okay, so this is in seconds. Now let's advance this and let's take a look at the heat produced. Hope all of this is right. So let's save it as okay. So something ran. Now there is the function that I want to tell you is called heat release rates. Heat release rate, I think. Gas dot heat release rate. Okay, so this function heat release rate gives you the heat released in this system through all of these reactions, all the reactions combined together in watts per meter cube, right? If you have to look at the heat released in an individual reaction, so again, let's take up the reaction number 11, then there's another function called heat production rate. So gas dot heat production rates, okay? And then we assign the reaction number, production rates, right? So heat production rates, okay. So this tells us that at this instant, at the particular temperature and pressure, and what is the temperature right now? Gas dot T, okay. Oh, sorry, R dot T. Yeah, okay, or the same thing. Okay, so at this particular point, the reaction number 11 is an endothermic, sorry, an exothermic reaction. It's a negative number, so the heat is being released. But now, if we were to if we were to add it all, so each reaction has its own heat release, right? And so when we sum up all of the heat, whether it is released or and again, sorry, I think I misspoke there. This is heat production rate. So this is the heat being produced from a reaction. Okay, so if we add up all of the heat from each of the reactions, it should be equal to the total heat from the system. Let's say if we sum, say NP, and this is where numpy comes in. So we say NP dot sum, and we sum all of these heat released by each and every reaction. So heat production rates okay. So if you see this number here is equal to this number here. So when we sum up this command here is summing up the heat generated by all of the reactions, all the 325 reactions in GRI mechanism. It's summing up all of them and then showing us that the total number is equal to the final heat release that was calculated by Cantera, right? So basically, I mean, there are these two equations that you could use if you want to know the heat released by the entire system, then you can use this function, heat release rate. If you want to calculate or find out the heat reduced by a certain reaction, then you use this function called heat production rate. All right, so that was it for this lecture, and I'll see you in the next series, which will be on flames. All right, thank you so much.